So, let us come to our 16th class on transport phenomena, TP 16. In this class, we will go through the kinetic energy correction factor for turbulent flow. Kinetic energy correction factor for turbulent flow. Now, let us consider the turbulent flow of a fluid through a circular tube of radius r, and the velocity profile is V is equal to V max into r minus r raised to the power 1 by 7. So, we have the aim to obtain the value of alpha for the present case. This is our task for the today's class, that if the turbulent flow type of velocity profile is being given, so how the kinetic energy correction factor can be evaluated in this case. So, we have the equation V is equal to V max into r minus r divided by r raised to the power 1 by 7. So, let r minus r, if I am assuming it is equal to y. So, V is equal to V max r upon r raised to the power 1 by 7. Sorry, r minus y upon r raised to the power 1 by 7. This is the typical turbulent flow velocity profile. So, what is the first task in order to go for the deriving the value of alpha? The first task is we have to for evaluating alpha, it is necessary to have an expression of the type where V average can be represented as a function of V max. So, this is the first task. Now, let us try to visualize this case using a diagram. This is the circular conduit. This is your center line. So, this plan view is like this. Plan view is like this. This distance is y, that is r equal y equal to capital R minus small r. This is your r, and this value is the small r. Sorry, this value is equal to small r, and the thickness of this strip is, let us suppose, dr. So, taking the plan view for having the flavor of the velocity profile. So, since this is a turbulent velocity profile, so this is the V max, this is your V max, right. This distance is r. At a distance y from here, I am taking a strip here. So, this length is dy, and this velocity is the representative instantaneous velocity v. This is the velocity profile and the corresponding diagram for evaluating alpha in the present case. So, referring to the figure above, figures, an elementary area dA in the form of a ring, of radius. What should be the radius of this ring? That is the r, that is equal to r minus y. So, of radius r minus y, so if I am assuming this r minus y, so this thickness should be dy, because y is changing. Radius r and thickness dy is taken into consideration. So, the value of dA, that should be equal to how much? 2 pi r into h, 2 pi r into y into dy. Rate of fluid flowing through the ring that is equal to dq, that should be equal to area of the ring, that is ring element into the local velocity, that is dq, that should be equal to area of the ring, that is 2 pi r minus y into dy, and what should be the local velocity? Let it be v into v. So, integration of dq between the limit 0 to q, that will be given by q, that will be equal to integration of this quantity from 0 to r 2 pi r minus y into dy into v. So, the expression for q comes as 2 pi r minus y into dy, and v has the form v is equal to v max into y by r raised to the power 7 integration from 0 to r, that should be equal to 2 pi, the constant should be evaluated outside, 2 pi v max, these are the constant quantity, into y by r raised to the power 1 by 7 into r minus y dy, integration from 0 to r, that will be equal to 2 pi v max divided by r raised to the power 1 by 7, okay, integration 0 to r minus y raised to the power 1 by 7 dy. That can be written as 2 pi v max divided by r raised to the power 1 by 7 into r into y raised to the power 1 by 7 dy 0 to r minus y raised to the power 8 by 7 dy integration 0 to r. That can be written as 2 pi v max divided by r raised to the power 1 by 7 into r raised to the power 8 by 7 is integration and putting the limit divided by 8 by 7 minus r raised to the power 15 by 7 divided by 15 by 7. So, q is equal to 2 pi v max divided by r raised to the power 1 by 7 into, we can write inside the parenthesis 7 by 8 r raised to the power 15 by 7, 15 by 7 minus 7 by 15 r raised to the power 15 by 7. So, that can be written as 2 pi V max into r raised to the power 15 by 7 minus 1 by 7 into this r 15 by 7 can be taken out. So, 7 by 8 minus 7 by 8 minus 7 by 15. So, this is 120, 105 minus 56, that can be written as 2 pi V max r raised to the power 2 into 49 by 120. So, the expression for Q comes as 49 by 60 So, the expression for Q comes as Q is equal to 49 by 60 pi V max r square. Let it be question number 1. If V average is the average velocity, if V average is the average velocity, then equal to A into V average, that is equal to pi r square into V average. So, we can proceed now as in terms of average velocity, so that the expression for kinetic energy correction factor can be evaluated. So, let it be question number 2. So, equating 1 and 2. So, equating 1 and 2, we are getting that the 49 by 60 pi V max r square, that should be equal to pi r square V average. So, the expression for V average in terms of the maximum velocity, that pi r square cancel out, that is equal to 49 by 60 V max. Now, the velocity profile can be written in terms of average velocity. Can be written in terms of average velocity as V max, that is 60 by 49, 60 by 49 V average into 1 minus r upon r raised to the power 1 by 7. Let it be question number 4. Let it be question number 4. Now, average value of this V cube, that is equal to 1 by A double integration over the area A V cube dA. So that can be written as so average value of this V cube, that will be equal to 1 by A, that is 1 by pi r square, integration 0 to 2 pi, integration 0 to r, (60 by 49) V average cube into 1 minus r by r raised to the power 3 by 7 r dr d theta. That will be given as 1 upon pi r square integrating theta, so 2 pi into 60 by 49 V average, that is whole cube, integration 0 to r minus r divided by r raised to the power 3 by 7 into r dr. That is the pi get cancel out. That will be equal to 2 upon r square into 60 by 49 V average cube, V average whole cube into the integration. Let it be question number 5. So, thus for evaluating alpha, integrand I needs to be evaluated first, Now I is equal to 0 to r minus r divided by r raised to the power 3 by 7 r dr. That can be written as now let z is equal to r minus r. Now let z is equal to r minus r. So now let z is equal to r minus r. So corresponding limits are when r is equal to 0, that is when small r is equal to 0. So what should be the value of z? The z should be r minus 0, that should be equal to r. This is your lower limit. When r is equal to r, implies that z is equal to r minus r that is equal to 0. So, that is the upper limit. So, the I, hence I that is equal to, and also z is equal to r minus r. So, dz is equal to minus dr. So, dz is equal to minus dr, that is the dr is equal to minus dz. So, I is equal to z divided by r raised to the power 3 by 7 and dr is equal to minus dz. So, minus integration from r to 0. So, that will be equal to integration from 0 to r. So, that negative sign can be removed by reversing the limit 0 to r, z by r raised to the power 3 by 7. So, I comes as I comes as 1 by r raised to the power 3 by 7 something missing. Okay, the value of r has been removed here into r dr, so dz into dr, and that should be multiplied into r small r, that is equal to r minus z. So, this should be written as r minus z dz. So, that will be equal to 1 by r raised to the power 3 by 7 integration 0 to r z to the power 3 by 7 into r minus z dz, that should be equal to 1 by r raised to the power 3 by 7 into r integration 0 to r z to the power 3 by 7 dz minus z to the power 10 by 7 dz integration 0 to r, is it not? That should be equal to 1 by r raised to the power 3 by 7 into r raised to the power 10 by 7 divided by 10 by 7. Minus z to the power 17 by 7, here should be 17 by 7, that means the r raised to the power 17 by 7 divided by 17 by 7. That should be equal to that should be equal to 1 by r raised to the power 3 by 7 into 7 by 10 r raised to the power 17 by 7 minus 7 by 17 r raised to the power 17 by 7. So, the I can be written as I that is equal to 1 by r raised to the power 3 by 7 into r raised to the power 17 by 7, that can be taken out, into 7 that may be taken out also, 7 into 1 divided by 10 minus 1 divided by 17, that is equal to 7 r raised to the power 17 minus 3 14 by 7, that is 7 r square into 170 17 minus 10, that can be written as 49 r square divided by 170, that is equal to 49 r square by 170. So, let it be question number 6. Now, from equations 5 and 6, now from the equation 5 and 6, the fifth equation was a relationship between the V cube average of V cube and the I. So, average value of this V cube, that may be given as 2 by r square into 60 by 49 whole cube V average whole cube into this I, that is the 49 by 170 r square. This r square will get cancelled out. So, that will be equal to 2 into 60 into 60 into 60 divided by 49 into 49, 149, that will be cancelled out from here, into 170 into V average whole cube. So, average value of V cube divided by V average cube, that should be equal to 49 to 49 V cube average, that should be multiplied by this quantity 49 into 49 into this 170, okay, divided by and upon which V average cube that is equal to 2 into 60 into 60 into 60. This this will get cancelled out, that is equal to 7200 divided by 7200 into 6 divided by 49 into 49 into 17, that will be equal to 1.058. Thus, the correction factor for a turbulent velocity profile that is equal to alpha, that is equal to the reverse of this, V average cube divided by VQ average, that is equal to 1 divided by 1.058, that should be equal to 0.945. So, if you change the value of the indices in the velocity profile for the different turbulent flow region, you will find that this turbulent value is slowly tending towards 1. So, in the case of the turbulent flow, it is often assumed that the kinetic energy velocity correction factor for the practical purposes may be assumed to be tending towards unity, whereas in the case of laminar flow, it is advisable that the correction factor needs to be taken as equal to 0.5. So, this completes your kinetic energy correction factor, overall energy balance, etc. From the next class, we will try to understand what are the fluidized bed and packed bed, what are the different parameters involved in the analysis of packed bed and fluidized bed, the well known Argon equation for the evaluating the pressure drop in the packed and fluidized bed, and also we will put some emphasis that what are the applications of the fluidized bed in the metallurgical industry, especially in the case of iron making and the sponge iron making, especially in the Indian scenario. These processes are of immense importance, where so many environmental guidelines are there, so many ceilings have been there with respect to environmental norms. So, within this context we will discuss those processes in detail. Thank you.